All right, welcome everyone to Order in Disorder, the foundations of chaos theory. I am absolutely thrilled to have you here for this explainer today because we are tackling a massive, genuinely mind-bending paradox. We're going to see how utter disorder, like totally unpredictable chaos, doesn't actually come from absolute randomness. No, it can actually emerge from perfect mathematical order. It's wild stuff, so let's get right to it.
Okay, let's dive into this. To really appreciate just how revolutionary chaos theory is, we kind of have to step back in time. Think back to Isaac Newton. For centuries, the absolute dominant scientific view was what they called the clockwork universe. Basically, the idea was that the universe is just a giant, highly predictable machine. The thought was, hey, if you knew the exact position of every object and the precise laws of physics, you could theoretically predict the future forever. And you know, it worked beautifully. It was perfect for calculating planetary motions or mapping the exact trajectory of a cannonball. But, well, as we moved into the 20th century, scientists started hitting a glaring problem. Some systems stubbornly refused to cooperate. Kind of like the local weatherman totally ruining your perfectly planned weekend picnic, right? Unpredictable systems, like the weather, just did not fit into that rigid, neat little clockwork model.
And really, the weather is the perfect example here. We've all felt the frustration of a totally blown forecast. It might be pretty accurate for tomorrow, but it's practically useless 2 weeks out. But why is that? It is not because meteorologists suddenly forgot the laws of physics. The atmosphere obeys the exact same physical laws on a Tuesday as it does on a Thursday. The real issue is that the atmosphere is this wildly complex system, packed with countless interacting variables. If you make even a microscopic error in measuring the starting temperature, the humidity, or the wind speed, that tiny, seemingly irrelevant error doesn't just sit there. It grows, it amplifies, it ripples outward until your forecast completely, totally diverges from reality.
So the crucial point is what scientists actually call sensitivity to initial conditions. Literally, if you take nothing else away from this explainer today, let it be that exact concept. It is the defining characteristic of any chaotic system. It simply means that two starting situations that are identical in every single way, except for maybe one almost imperceptible microscopic difference, will eventually produce entirely different outcomes. You've probably heard the popular term for this, the butterfly effect. It was coined by the meteorologist Edward Lorenz. The idea is a butterfly flapping its delicate little wings in Brazil eventually sets off a tornado in Texas. Now obviously, a butterfly isn't literally powering a massive storm, but it perfectly illustrates how a chaotic system takes a tiny disturbance and just magnifies it into a completely massive event.
To make this abstract idea a bit more tangible, imagine you're trying to balance a ball at the absolute, perfectly pointed peak of an incredibly steep hill. If you place that ball even a fraction of a millimeter to the left of the exact center, gravity takes hold and it rolls all the way down into the left valley. But if it starts a tiny fraction of a millimeter to the right, it ends up miles away in the right valley. The initial difference in where you placed that ball was so incredibly small you literally couldn't even see it with the naked eye. Yet the final outcomes couldn't be more different from each other. That is exactly how chaotic systems behave. Those tiny differences that we usually just brush off as insignificant rounding errors, over time, they become the only things that matter.
And so, this brings us to a massive question, one that completely shifted the scientific paradigm. We look around and we see all this incredibly complicated, messy, unpredictable behavior in the world. Things like a hurricane or a wildly fluctuating stock market. Does that immensely complicated behavior actually require equally complicated causes? Do you need a million rules to create a million variations? Well, let's zoom in from the macro world of weather systems all the way down into the focused, microscopic mathematical engine of chaos to find that answer.
The answer to that question is a resounding no. And the absolute best proof we have of this is called the logistic map. I really want to spend a moment here focusing on this because the logistic map formula is basically the secret decoder ring for all of chaos theory. It's an equation originally created by biologists just to model simple population growth, but the elegant math behind it is where things get crazy. The formula is conceptually so simple. It goes like this. Next year's population equals the growth rate times the current population times 1 minus the current population. That's it. It's just basic arithmetic, multiplication and subtraction, but it creates this beautiful built-in tension. See, one part of the equation drives the population up, that's your growth rate. But the other part, the 1 minus the current population, represents starvation or a lack of space, and that pulls the number right back down. So you take a starting number, run it through this formula with that single adjustable dial for the growth rate, and it spits out the next year's population. Then, and this is the crucial part, you feed that new number back into the exact same loop and repeat. Basic arithmetic. But the formula produces something absolutely magical.
Let's move to and see how this builds, because this is where the magic of the logistic map really happens. Imagine you start turning up that single parameter, that growth rate dial we just talked about in the formula. At low numbers, the population just settles into a completely stable state. It hits a number and stays there. Boring, predictable. But turn the dial up a little more and suddenly, boom, that stable state breaks. The population begins bouncing between two different values year after year. High, low, high, low. Turn the dial up just a microscopic fraction more and it splits again. Now it's alternating between 4 values. Turn it a tiny bit more, it splits to 8, then 16, splitting faster and faster in a process scientists call bifurcation. And then, suddenly, the system crosses a threshold. The pattern vanishes entirely. The population jumps around wildly with absolutely no repeating sequence at all. Full, unpredictable chaos. And remember, this is all happening just from slightly tweaking that one growth rate number in our simple little logistic map formula.
Just take a breath and think about what that actually implies. Complexity emerges from simplicity. Nature doesn't need complicated, convoluted rules to create highly complicated, unpredictable behavior. Sometimes all it takes is an extremely simple mathematical rule, like the basic arithmetic of our logistic map, repeated over and over again, feeding back into itself until it explodes into the wildest variations imaginable. It completely shattered the old idea that if something is hard to predict, we just don't understand the rules well enough yet. Actually, scratch that. Sometimes we know the rules perfectly, and the rules themselves are what generate the chaos.
And this brilliantly illustrates another massive twist in our story. Even when a system descends into full, unpredictable chaos, it isn't actually a total free-for-all. Chaotic systems are bounded by these hidden structures called strange attractors. If you actually trace the chaotic data points over time, they don't just form a messy, random scribble. They form incredibly intricate, bounded geometric patterns, like these endlessly looping butterfly wings. The system never, ever repeats the exact same path twice. That's the unpredictable chaos part. But the path it takes is always, always constrained within the invisible shape of the strange attractor. It proves that within the wildest disorder, there is a stunning, underlying order.
And you know, once scientists figured out what to look for, they started seeing chaos and strange attractors everywhere. This isn't just about the weather or rabbits breeding in a biology model. This exact math governs fluid turbulence in rivers and oceans. It maps out the wildly shifting balances within global ecosystems. It appears in the flow of electrical circuits, the precise timing of chemical reactions, the rhythmic beating of the human heart, and yes, even the supposedly clockwork motions of planetary orbits over billions of years. In fact, many systems in nature operate right on the razor's edge, that boundary between rigid, boring order and completely random white noise. Because that boundary, that's where life and complexity actually happen.
Which leads us to what is perhaps the deepest, most philosophical lesson of chaos theory. Predictability and determinism are not the same thing. Let that sink in for a second. A system can be entirely deterministic. That means its future is 100% locked in and determined by its present state and the exact physical laws governing it. The universe isn't just rolling dice. But, and this is a massive but, just because something is deterministic does not mean it is predictable by us. The rules are absolute, sure, but our ability to measure the starting conditions perfectly, that's utterly impossible.
It is a literal balancing act. On one side of the scale, we have exact physical laws. On the other side, tiny uncertainties. And in chaotic systems, the tiny uncertainties tip the scales every single time. This fundamentally changed how science looks at the natural world. It proved, once and for all, that there is a hard, physical limit to what we can predict. And that limit isn't because we're ignorant or because our supercomputers aren't fast enough or because we haven't discovered the right math yet. No, the limit exists because of the intrinsic behavior of nature itself. Tiny errors are a physical reality, and in a chaotic system, tiny errors will inevitably overwhelm any forecast.
So, as we wrap up this explainer today, I want to leave you with this final provocative thought. Chaos theory is humbling, for sure, because it tells us flat out that we can't predict everything. But it's also incredibly inspiring. It teaches us that intricately wild behavior springs from the most orderly, simple foundations imaginable, just like that basic logistic map formula we looked at. So the next time you look at something that seems totally random and overwhelmingly messy, whether it's a massive storm system, a murmuration of birds, or, hey, even the trajectory of your own life, ask yourself, where else does hidden order exist within seemingly random events? What strange attractor is pulling the strings just beneath the surface? Thank you so much for joining me to explore the beautiful architecture of chaos. Keep wondering, keep asking questions, and I will catch you in the next explainer.